right, good afternoon, everybody. Let's go ahead and get started. We are within our time box. And since Agile is all about time boxes, let's go ahead and keep this one here, okay? Thank you for coming to the talk today. I have the pleasure to introduce David H., who is going to be talking to us about MLOps and Agile practices. If you don't mind, please, at the back exits are QR codes for surveys for the discussion and for the event as well. Other than that, thank you guys for participating and attending, both in person and virtual back there on the Zoom. If we can do anything to make your experience better, please reach out to somebody in one of these black shirts and we'll get you taken care of. With that being said, I'm going to hand it over to David.
Thank you, Lee. Appreciate it. Can you all hear me okay? All right. So thank you, everybody. Good afternoon. Good morning for those of you who may be in the West Coast. My name is David Hendrawirawan. I'm currently an adjunct faculty member at UT Austin, where I teach data governance, AI governance, cybersecurity law, and the human dimensions of cybersecurity. I've previously been a consultant with Deloitte, been an enterprise architect at Dell, and have done currently independent consulting still, invested in education. I'm a business owner. I have a coding franchise for kids called Code Ninjas, where we teach kids how to code. So enthusiastic about it. I think COVID has done a lot of good things or bad things to people, but in my case, it oriented me to take time away from kind of my bread and butter consulting to invest more in the future generation. That is the reason why I'm teaching at the higher education as well as the K-12 level. The COVID has demonstrated that our education system is often is very prone to disruption. Things are getting better and better now, but at the same time, so it's been a valuable experience the past couple of years, and I'm actually now starting to head back more into doing my bread and butter, which is why I'm excited to be involved in KAA Austin Agile conference such as this one. So I'll talk today about the importance of Agile practice in the context of machine learning or AI. I think nowadays there's not a day pass without you hearing something in the news about AI. And so I hope that AI is such a big topic and it can mean different things to different people. So I hope that this will be just one of the primer, because this definitely shouldn't be the last topic that you'll hear about how you can apply the Agile discipline to help address some of the inherent issues with machine learning. So what we will talk about today, first, I will start with giving you a context. What are the inherent issues? We hear a lot about challenges with AI or machine learning and how we can gain trust in these type of systems. But from the development, what are the inherent factors that cause this to be so? And then I'm going to give a little bit of a primer on AI or machine learning lifecycle process so that we can dissect it further and understand better in terms of the process and the mechanics and the typical challenges within the pipeline itself. And then I will share some overview of Agile techniques and practices, which is typically called MLOps, some of the components of MLOps that can actually address some of these inherent challenges, okay? Would love for this to be as interactive as possible. Feel free to stop me at any time. Just raise your hand if you have any questions. And toward the end, I will also allow some room for questions. Out of curiosity, how many in this room has done data science? Data science work, yep, okay, as I expected. Data engineering, okay. Project and program management, yep, that's gonna be the majority, good. Data analysis, BI, reporting, okay, good. This is the exact composition that I'm thinking. So now, majority of us have, but I'm sure, even though we may not have been a data scientist or data engineer, we have worked with one of them, right? Nowadays, a lot of systems project, and that's my background as well. So I have a degree in business, but also in MIS. I have worked with data engineers, with the IT security people. I've worked with many different personas. And so that gives me the advantage of having a non-siloed perspective of how we solve these problems. And data scientists, data engineers, they have great expertise, but oftentimes the reason why most machine learning or AI projects do not succeed is because of silo and because of lack of agility or interdisciplinary approach. Okay, so but first let's talk about what do we mean by trustworthy AI or machine learning. AI, artificial intelligence, can mean different things. A lot of people in the public now thinks of AI because it's popularized by OpenAI with ChatGPT and other generative AI. So distinguish generative AI, which is the things that can create text, image, video, versus traditional AI, which could, and for the most part, traditional AI is not too new, and it's actually been done by a lot of companies. And machine learning, as well as the use of digital technologies such as IoT and mobile apps, sensors, etc. Those are also what I consider to be a part of this whole talk. Okay, but when we talk about trustworthy AI, what do we mean by that? And so, a trustworthy AI system has to have reliability, meaning the output is reliable, is accurate, is stable, it's consistent over time, right? You don't want it to say one thing one day and then the next day you have unanticipated data or new, greater volumes of data, and suddenly the prediction skew to one way or the other. And it needs to be fair. It needs to be free of bias, or it's not never really going to be free of bias. That's impossible. But you need to be cognizant of the biases, both explicit as well as hidden biases in your data. Because inherently, machine learning and AI is the application of bias. You take a sample data, a subset of data, and then you learn from that data, and then you extrapolate the result to the entire population. What do you call that in English? Stereotyping, right? That is the very essence of bias. And when people say, "Oh, AI has bias," of course, that's we are intentionally engaging in bias. The question is, are you applying that bias more accurately or less accurately against certain segment of the population? And that's the reason why it's a continuous process. You have to continue to monitor it. You have to continue to address it. Okay, safe. What do we mean by safe AI? Safe means that it's secure against attacks. The nature of AI and ML system is such that it opens the door for new types of adversarial attacks. Even if you have applied your traditional cybersecurity controls over your data, over your application, over your API, the inherent nature of AI is such that it's open to new types of attacks, which I will go into more detail later. Privacy, it needs to make sure that any personal data within the training data as well as the production data is protected. Because if you're not careful, the model could recall or remember sensitive information that exists in its training data and can expose it to the when you're deployed in production. It needs to honor intellectual property, right? The input needs to be legitimate and legally usable, free of copyright issues. And finally, it needs to be transparent. An AI system needs to be auditable. People need to be able to understand the lineage of where the data came from, what process was applied, which model was chosen. It needs to be explainable, meaning when it gives a certain prediction, we need to be able to understand why it's doing that, which input variables are the most impactful to produce this particular recommendation, for example. And it needs to be traceable. At any given point in time, you need to be able to track this model was produced or was trained using this version of the data. And when I say version of the data, because unlike traditional system, the data changes all the time, and it's called drifts, which is what I'm about to talk about. So against all of those objectives, there are many inherent issues, but I'm classifying them as the top 3. I've studied many different inherent challenges, and these are not exhaustive, but if I were to think about what are the top 3 things that Agile practice are specifically potent to address, I'm highlighting these top 3 challenges. Number 1, drift. The nature of AI system is, and machine learning, is that it is highly dependent on the data that you use to train it, which, by the way, continues to evolve. Data patterns will change over time, and it's due to various reasons. The inherent content itself changes, the technology that used to capture data changes, the resolution, the capability, and all of those things, and the cyclicality of real life cause data drifts or model or concept drifts. And so it's an ever-changing. You never just, in the typical system, you deploy the data, you test it using test data, and then when you launch to production, it's done. With AI and machine learning, it's never done. You're never done. You're always going to continue to monitor and update your model on an ongoing basis, because that model will get worse over time. Adversarial attacks, as I mentioned, the nature of AI and ML system is such that it can be interrogated by people, and that interrogation, even if you have the right, supposedly the right user using it, you could potentially engage in ways that can circumvent the model in such a way that you could expose personal data within the training data population in a way that you could potentially steal the model, meaning you can reverse engineer the model. A model is an intellectual property. A company invested in order to build that predictive model. So it can be reverse engineered if somebody can keep running queries against it, looking at the output, and then say, all right, I'm going to try to build another model and see if my built-up model can replicate the same result. And if so, then I essentially have stolen this model, right? There's also evasion attack, where somebody can inject something in their input data in such a way that the model may not detect. So if it's a fraud model, for example, somebody could manipulate the input data in such a way that they can stay under the radar. And finally, the complexity of the pipeline. So this is one of the things that's preventing most POC or proof of concept from getting to production, is a lot of the data modeling, the data scientists are focused on the modeling. And that used to be the roadblock, that used to be the bottleneck, which is the data science skill. However, nowadays, majority of the issues in order to scale and produce an AI system is no longer with the lack of modeling capabilities. It has to do more with the lack of capability to create a repeatable process, to clean the data, to prepare the data, to retrain the model. Okay, and those things are often underestimated. So let's talk about the complexity issue. As I mentioned, most of the time, data scientists or data science discipline think of AI from the perspective of the machine learning code. But the machine learning code itself is actually just a small piece of the whole puzzle. Okay, there's data collection, there's a code to collect data from different sources. There's data verification, there is feature engineering, or it's a different term for it, is data wrangling or data preparation. You don't just feed the data into the machine learning, you have to prep it. If it's image, you have to encode that image and turn it into digitized version numbers that can then be fed into a deep learning model. There is configuration and automation for all of these things. There's testing and debugging. The number of testing that you have to do in a machine learning system is far more complex and more interdependent than your traditional, typical deterministic application development cycle. So all of these things, and plus, once you get to production, again, there is no such thing as production versus dev in machine learning. Yes, there is the environment, but what I meant is, as a life cycle, you don't stop after you launch to production. That cycle of, all right, we can deploy and we're done. No, that once you deploy, to monitor it, because by definition, a model will degrade over time due to data drifts and other inherent reasons. Okay, so if we look at traditional system testing, this is probably what most of us are familiar with, right? We have the development system, the code in the development, we unit test it, we do integration testing, and then we deploy it to production. And then we have some kind of system monitoring in ops. Well, a machine learning system, the model is dependent on the data. Okay, in a traditional system, you have roughly the same data in development and production, right? So, or you take a production data and then you scrub PII out of it, you use it to test. You have price times quantity equals total sales. That's it. But in a machine learning or AI model, it depends on the distribution, the statistical characteristics of your training data, which can change over time. So not only do you have to do the unit test, integration, and system monitoring, kind of the infrastructural or application layer, you also have to do data test. You have to perform statistical tests on that data. So you have to understand a little bit of that statistics. And as nowadays, most of us are not necessarily trained in the data science, but many of us are starting to feel that we have to be familiar with the language and the paradigm, right? So there's such a thing as outliers, for example. What a lot of data scientists do, or data science task, has to do with looking at the data and making sure that you eliminate things that are outliers, because those may affect how your model behaves in an unstable or extreme way. So they don't like extremities, right? They like to stereotype. They like to say, all right, for 80% of the population will follow a certain pattern, that's what we want to predict. So there are model tests, Q-ness tests, and then when you start to use that data to train your model, you then have to look at the output of the model. You have many different model choices, you have many different data versions, and then you have to essentially run a continuous cycle of experiments. That's the very essence of a model ML lifecycle process. It is very complex because it involves many more personas. You have the data scientists, but you also have the data engineer. You have the lawyer, you have the legal team, the person who has to deal with governance issues, right? Is this data appropriate? Does it contain PII? Does it contain copyrighted materials? And you have the product engineer, site reliability engineers. There's a lot more that has to happen in order to deploy a machine learning solution, a model. So the second inherent issues that we talked about is drift. Data drift is changes in statistical distribution. And this happens over time, or this could happen in cases where your training data set is different from your production data set. Or it could also be because when you're developing a model, whatever your training data, you have to split that. You have to split that into a subset that you use to train the model, and then a subset that you use to test the model, and a subset that you use to then validate the model. And so if you distribute your 100% of your data, let's say, into 60% for training, 20% for validation, 20% for testing, you have to make sure that the distribution of each of those segmentation are consistent. If they're different, then you have skewed results. Okay, so that's the definition of data drift. Concept drift, on the other hand, is where you have multiple features. A feature is a variable, right? Price and quantity, for example. And in this case, let's take an example of spam, all right? So just making this as an example, perhaps the two features that may be an indicator of spam is the number of grammatical mistakes, okay? And that's the first feature, right? The more grammatical errors, the more likely that it's a spam. And perhaps the second feature would be the use of certain terms such as buy this, you'll get rich, or whatever, right? So certain keywords, right? Now, over time, it used to be that the relationship between the number of grammatical mistakes and the number of certain key terms may indicate this particular pattern on the left, but over time, the generation, the younger generation tends to communicate in a way that is more informal. It's funny, one of the student have a communication with me, and the student didn't mean anything bad by this, but it was regarding a grade. So he seemed to have less than what he anticipated. So his email starts with, "Dear Professor such and such," and then the next sentence is, "Wait, what?" And then I didn't expect that, my grade is such and such. So, and I said, oh, okay, so that's just how they communicate. So nowadays, the more grammatical errors doesn't necessarily mean that it's a spam. That's just the way people communicate, I guess, these days. Okay, so the relationship between these two factors have changed. So your model has to change. Otherwise, you would be misclassifying legitimate email as spam. So that's concept drift. So drift, so now models also have accuracy score. So you can calculate, for example, when you predict something, when you run an input data and it predicts this is a spam versus not, and then you know what the actual result is, that's model accuracy. So model accuracy are things such as the rate of false positives or the rate of false negatives compared to the rate of true positive or true negatives. There are different measurements that you use to look at how accurate this model behaves. But just measuring the model accuracy is not enough, because the drifts often precede a model issue. Okay, so when there is a drift, your model's prediction will eventually veer away. Your model quality will eventually degrade, but it doesn't happen right away. So if you're only monitoring the model accuracy, and let's say in week 3, you detect a drift in week 2, the model quality will not degrade. You will not see that model degradation until week 3. Okay, so this is the reason why you have to detect the drift before the model actually degrades. Otherwise, it would be too late for you to trigger the automatic retraining of your model. Okay, so drifts can happen in a sudden, it can happen gradually, it can happen incrementally, or it can reoccur, such as in an event when there's cyclicality. Okay, so every time there's Thanksgiving or Christmas, then the patterns of the customer will change. Okay, and that's the reason why, again, cyclicality, economic cyclicality, when there is recession versus high inflation, these things will cause drifts in the data, and your model will have to be adapted accordingly. And this is, again, an example where just inherently, the model performance will degrade because of data or concept drifts. And because of that, you have to plan, and you know for sure there's no such thing as deploy to production once and done. That model will, it is only a matter of when, not if, when that model quality degrades to a certain level. So you have to set that threshold. When the rate of false negatives or false positive exceeds certain level, that's time for you to retrain the model. Okay, and then increase the model accuracy again over and over and over. All right, so then the third type of inherent issue is adversarial attacks. So there's model poisoning attacks. So when in the training data, somebody can sneak in information that will cause your model to behave a certain way. So let's say you have a model. So let's say you have a sensor, okay, in your neighborhood, in your house, and you can detect if somebody's coming in front of your house. Nowadays, we have those Ring or like the technology that can detect potential intruders into the house, okay? So model poisoning is as if somebody who's trying to come at 3 a.m. in the morning and bring a dog and let the dog pass through in front of your house, okay? So this will cause your detection system to think, oh, a dog, at 3 a.m. in the morning is normal. Somebody has a dog in the neighborhood, okay? Now, and then you go to the evasion attack. So because of that, now at 3 a.m. in the morning, now this thief knows that at 3 a.m. in the morning, if he puts on a dog costume, right, he will likely be able to stay under the radar. He will be able to be undetected, okay? So that's model evasion here. It's causing the prediction to be incorrect, okay? Now, extraction attacks is where, you know what, now this thief is gonna start saying, all right, let me put a dog, let me put a rabbit, let me put a cat, and see what kind of, how does this detection system work against different kinds of animals. And finally, inference attacks. Inference attacks is where they, through the same dynamic, by running query after query, it can deduce that the model was more sensitive toward dogs and cats, so animals that have whatever, like certain shape of an ear. And so they can infer that most of the training data came from a database of dogs and cats, for example. Okay, so that can expose privacy. See, like these things didn't, I mean, even if you have the most secure data protection controls, access control, you've already encrypted your data, you've already applied data loss prevention, firewalls, etc. The people can still jailbreak your AI model essentially, okay, using these techniques. So some of the examples is, here's a model evasion example where the picture of a panda and somebody just embed this pattern here over to the pandas, and suddenly the model that would have been accurately classifying the image as panda is now classifying it as a gibbon with a high level of confidence. So that's an example of an evasion attack, okay? Now you can't see the image because the resolution is too low to see the difference between the left panda and the right panda, but the right panda essentially has this pattern already kind of superimposed on it. We just can't see it with our own eyes, but computers can, because computer can see a much deeper resolution. And then another example of the model evasion attack is when these researchers have figured out if they put that patch, right? So that patch will cause the model that's supposed to be able to detect a human being to miss out that this is a human person, okay? So these are new types of evasion attacks. So how do you solve that? Well, you have to apply backdoor detection. You have to detect if somebody's trying to manipulate your model by continuing to rerun queries after queries. You have to do adversarial testing. You have to actually try to penetrate test your own model by applying some of these attacks itself before you actually launch the model, etc. And the same thing, you have to continue to retrain. It's only a matter of time before somebody will figure out how to take advantage of this model's inherent weaknesses. Okay, so let me just pause to see if there's any question. I've been saying the bad news. Now I'm about to go to the good news, or how do we understand this thing? Any questions so far? Yes. Yeah. Yes. Yeah. Yep. So good question. So training the model itself is not that easy, right? So you have to have somebody who understands statistics, data science, to be able to say that, hey, you know what, under these circumstances, these are the F1 score or whatever. There's lots of metrics that will indicate whether the model is accurate or not. Okay. Now, what causes drifts oftentimes is just, it may be the changing consumer preferences. It may be changing technology. So for example, we used to have, so there is a case when somebody's using machine learning to study voice recording of people in order to detect emotions, okay? But the training data came from the 1980s, 1990s, when you were using different type of recording devices, right? And over time, now a lot of people are using their phones to record things, so the quality changes. So when you run the model that you developed using the 1990s data versus the exact same person in the 2020s, the model predicts differently. So for example, so those are just examples of drift. Yeah. Yes, sir. It may, and I think to your point, that's why the definition of AI, we have to understand the decision model, if it is a deterministic decision model where you already pre-coded the logic, no, it's not exposed to that. But if it's a decision model that learns from the data, where you have to feed some underlying data for it to learn, then the more likely that it's going to be exposed to the same inherent limitations. Yes, sir.
That way the people in the Zoom conference can hear as well.
So if we know there's going to be drift and we have to retrain it, why isn't it not just a continuous process of retraining it constantly?
It should be, but that's the reason why data science did not start with that, right? Data science, data engineers are more, your question came from an engineering mindset. An engineer like to be able to create something that's repeatable, right? A data scientist, and this is not a knock on data science, it's just the way our education system and the discipline has evolved over time. Now it's maturing more, where that's the reason why the term MLOps is now emerging, right? That they're saying that we can't just teach our future data scientists to think in an artisan way, to work in artisan way, where they just use Jupyter notebooks on their own desktops, right? It's almost like using Excel to do your ETL. For those who are data, ETL is a system to extract, transform, load your data. You're supposed to use a much more robust tool than a Microsoft Excel, where there is no data integrity controls whatsoever. So I guess, thanks for your question, because that's affirming why we're having this talk. We should be creating that data pipeline in a more repeatable patterns, using the repeatable tools and processes. Yeah. Last one, and then I'm going to move on. Yes, please.
Here you go.
Thank you. So I coach I coach an engineering organization,
Yes.
and this is fascinating to me because I'm the one sitting there saying, I need y'all to learn people.
Yes.
Because what's going to happen is you're going to build a model and society is going to change and you're going to miss that.
That's right.
So I've been bringing in people who are non-data scientists,
Yep.
who are a little bit more on the business side and the psychological side to work with our data scientists.
Yes.
So you just made me feel better. So thank you.
Oh, thank you. No, I appreciate that. And that's exactly the challenge with a lot of this. Everybody's excited about AI, but the conversation that happens a lot at times are still at this very thin, like 0.01% of the population. And so the rest of the population feels like they're just talking to each other, and the general public don't understand what's going on. And so, yeah, I appreciate what you're doing. And I'm trying to do the same thing, trying to essentially share this with students, share this with kids. One of the most interesting projects we did was the graduate students that I teach at UT. I asked them to create a cybersecurity awareness training for kids at Code Ninjas at K-12. So we deployed it to students in the US and UK. And it's an interesting project. And they actually enjoy that process. So I think what you're onto something here. We're onto something. All right, so let's move on to so I'm going to give a little bit of a life cycle primer, but I don't want to take too much time in this. Like a lot of these materials, I'm taking this a lot from AWS and Google and Azure. All of them, if you Google MLOps and then, or machine learning, ML lifecycle, and then one of those three, they already produce a lot of good white papers and patterns and materials on it. But just to kind of anchor us, here's a typical life cycle for machine learning or AI systems development. We start with a business problem. Somebody said, I would like to build a model that can predict fraud. Okay, now you frame that problem. What are the different models? Are we using regression? Are we using supervised versus unsupervised learning? Which machine learning techniques should we use? What type of data should we use to feed into this type of model? Then you collect the data, you prepare that data, and you do what we call the feature engineering, which is oftentimes also called data wrangling or data preparation or data pre-processing, which is essentially reformatting or putting that source data in such a way that it's ready to be fed into machine learning. And then you train your model. Now, when you do model training nowadays, there are lots of different models. And so MLOps allows the data to just essentially do a brute force by feeding your data into so many different alternative models and then presenting the machine learning, the data scientist with the output. The output of here's the top, out of 100 or hundreds of models that we just brute force run this data against, train this data, here are the top 10 different models. This particular regression model, this particular decision tree model, this particular random forest model seems to have the best outcome. And then they do parameter tuning where the data scientists then look closer at this. Okay, between these 3 different models, potentially these 2 types of models are the most effective, but I have to tune the parameters. And so when they tune the parameters, they evaluate the effectiveness. If I increase certain parameter, does the model become more accurate or less accurate, more stable or less stable? And there's a lot of trade-offs there. The more accurate the model, the better. But if you're too accurate, essentially you may be committing what they call overfitting. Overfitting is your model follows your training data. And as I mentioned, when you train the data, you also have to set a subset of the data that for testing and validation. If the distribution of those data are different, that is essentially the same as having a drift, right? You're training the data using data that's distributed one way, but then the real world is distributed a different way. And so your model is accurate for certain type of distribution, but not for the other type. And so if you're there is such a thing as being too accurate within a model, okay? So, and then, as I mentioned, once you build your predictive model, their prediction is production. So that's what you actually fed the real production data. Now you have a new transaction comes in, the prediction service will say it's fraud with the 80% likelihood versus it's a non-fraud with a 43% likelihood, okay? That has to be monitored on an ongoing basis. So, and if we take there are 3 dimensions to this whole pipeline. There's the data dimension, there's the model, and there's the code, okay? Now, traditional systems, you just think code, right? Development code, testing code, and then production. Well, in machine learning, you're dependent on the data. As I mentioned, there's the training data. You have to take your training data set, and then you have to break it into 3 sections: for training purpose, for validation purpose, and for testing purpose. And then you have metrics. Metrics is also data. So essentially, once you run each of these data against the model will produce the outputs, and those outputs are in the form of metrics. And that indicates how accurate or how stable that model is with that particular data. Then you have, once you go all the way to the deployment and you run that particular model in production, you have production data, which may be completely different, right? Your training data may came from historical data over 20 years ago, and your production is the data that's fresh today, okay? Model. Again, you start with many candidate models when you first started to choose which model you want to use before you start to tune it. And when you have some of the metrics, then you have a narrower set of model candidates, then eventually you will tune it to become the deployment ready model. And the code, you have the code that you use to pre-process the data. A lot of that is more Python and SQL to prepare your data. And then you have the training code. That's what allows you to run the data against your model training. And then you have the inference code. This is the final code that finally says, okay, this is what we run in production. If you put it all together, it becomes very complex. And it becomes very, very interdependent. So what are some of the inherent issues that we see in this kind of pipeline? Most of the times, data scientists use unintegrated tools, things that are not repeatable. So it's very difficult to share models and artifacts. And when you have multidisciplinary teams, cross-functional teams, it's very difficult to move things around. The data evolves and drifts, which is why it requires robust versioning. Most developers are not used to keep track of data version. They keep track of code version, but they're not accustomed to maintaining data versions. There's interdependence. When you change one model parameter, it will change downstream impact. A lot of machine learning is not one model, it's multiple models. The output of one model becomes the input for the next model and the next model and the next model. You can't reproduce the model because you don't keep track of, okay, which one? There are multiple versions. It's not just one model. You have 10 candidate models, and each of them may have 10 different versions, depending on what parameters you enter into it. And each of them has to be tracked. So it's very, if you don't have automated logging, automated monitoring, you won't be able to automatically retrain, as the gentleman asked before, right? So it's very inefficient and error prone. So what are some of the MLOps techniques? There are multiple of them. I'm going to cover 3 that are popular nowadays. So one is experiment tracking. Experiment tracking, so machine learning is a iterative, continuous experimentation-based process. It's a metrics-driven process, okay? Unlike before machine learning, people use deterministic decision systems. I think one of the gentlemen asking, right? So if in a deterministic, you use human intuition to say, okay, the input should be like this, and this is how we should calculate it. With machine learning, we don't care how the machine calculates. We just know that there's a library of different models. We'll just brute force run our data against it, and then identify the ones that seems to be the most accurate. Out of hundreds of different models, here are the top 10, and then let's tune the parameter for each of that and see which one can be better than the others, right? All of those have to be tracked. It has to be, you have to essentially maintain different versions of it. This is an example of an experiment tracking dashboard that shows many different, the baseline, as well as the different experiments and what kind of parameters and metrics that is produced under each. Observability. So the term observability is essentially monitoring. There's data observability, there's systems observability, and there are a lot of already standard measurements and metrics in data science that can detect concept drift, that can detect bias, that can detect feature attribution or explainability, okay? So these things have to be embedded into your process. You don't want to do this manually or as an afterthought. You wanted to deploy it from the get-go. And some of these metrics are more complex than the other. So you need to understand it again. You need to have the more fundamental metrics, such as your system logs and tracing, before you can then measure the freshness of the data. And once you have the freshness of the data, then you can begin to measure more complicated measurements, such as model accuracy, etc. End-to-end automation, as mentioned, again, like there's multiple codes. There's the code to manage your data that has to be automated. There's code that then deploys that and then redo it every time you choose a different experiment. So there are multiple. So in the typical development lifecycle, we know the term CI/CD. How many of you have heard that, right? Continuous integration, continuous deployment. Very popular, very common. In the machine learning system, it's CI/CD/CT, continuous training, right? So you deploy CI/CD, you deploy CI/CD to do your data, to do your testing, to do your training, and you essentially that you kind of wrap another layer around the CI/CD pipeline. By the way, this automation doesn't happen overnight. It's very difficult. Most organizations today have not reached the level where they want to be, which is right here, when at least the ML pipeline is automated. Most people are still in the manual phase where you have either ad hoc POCs or manual model serving process, right? So just understand that this is a journey. It's not going to happen overnight. If you're working for an organization, don't believe if somebody said, we have the magic tool, the silver bullet that's going to automate it from day one. Most of these tools are still very much disparate. It's still in the early stage of integration. But the important is not so much the tool, but the mindset of the people who work in these projects. So the key takeaway is, again, the machine learning AI lifecycle is a continuous metrics-driven process. It is prone to new adversarial attacks, and the components are much more complex, dynamic, and interdependent. Agile practices is a potent solution to address these 3 inherent challenges. Examples of that is experiment tracking. Again, Agile is always continuously improvement mindset. That goes along with the concept of experiment tracking. Observability. Again, you can't manage what you don't measure. So that's important. And finally, just continuous automation using tools. Okay. So with that, we're almost right at time, I guess.
Yeah, we're down to within just the last minute or two. So do we have one or two more questions for David before we have a bunch? I'm going to go right here and then one more up here. Okay, good. Access to the slides. My understanding is that, yes, we will be putting them online. We don't have that set up right this moment, but we will be communicating with all the attendees where to get those. Okay.
On your role slide, you had project and program managers up there, I think. And could you give an example? It wasn't on this slide. I think it was earlier. That was it. Or process management. Sorry, you have process management on your next slide. Back to maybe. Process management. Can you give an example of where process management would specifically fit in ML and AI?
Yes. So, so let's take this as this process right here, right? So as you can see, it's iterative, and we don't have the people persona in this, but the people who are involved in each of these stages. There's data scientists, there's data governance, etc. So it felt like a matrix. It felt like football player playing basketball, essentially, right? So you have to understand, how do you regurgitate all of that process, and it cannot be waterfall for sure. And it cannot even be just your traditional Agile, because traditional Agile is looking at one dimension, the code itself. But in this case, you take changes in your code with changes in your data, with changes in seasonality in production, right? So there's more, yeah. So I think process management, essentially, you have to take up your game in process management. It cannot just be an afterthought anymore.
Okay, and with that, David, thank you very much for the talk.
Thank you very much.
Hugely
Appreciate it.
interesting. One more quick reminder to everybody, please fill out the survey forms. QR codes are back there and on that door out there. Other than that, lunch. I mean, you guys are okay with lunch, right? Everybody good with that? All right, thanks folks for the attendance.